complex numbers, specifically the origin of this field of numbers. We'll be also understanding what do we mean by a field, which is quite a central topic. But before we get to that, I would like to talk about something, and that is that we must realize that in the historical and psychological development of mathematics or any other field in general, all these extensions and new inventions were by no means the product of some one individual's effort, right? They appear rather as an outcome of a gradual and hesitant evolution over time through various concepts and the build up to the actual subject. And the journey of complex numbers has been pretty similar. That's what we'll see here. And and to begin with, complex numbers is used to solve quadratic equations, but we'll start with something much simpler, that is a linear equation. Let's say a linear equation, say x equals b. It's a simple one, where x is the unknown quantity that is to be determined. The solution is simply, in this case at least, x equals b upon a, uh, given that a isn't equal to 0, right? And the requirement that every linear equation with integral coefficients a and b shall have a solution necessitated the introduction of a set of numbers. Sorry about that. Of a set of numbers known as, I guess it's denoted by Q. It's called the rational numbers, and this is conventionally known as the P by Q form of numbers, right? And so, to find the solution of that equation, we came up with rational numbers so that we could solve this equation. And then time went on, and we encountered different kind of equations such as, let's say, x squared equals, let's take 2, make it simple. X in this case is root 2, which obviously isn't a part of rational numbers. So since it has no solution in the field of rational numbers, that led us to construct a wider field of real numbers, denoted by the letter R, real numbers, in which a solution does exist. But even the field of real numbers is not wide enough to provide a complete theory of quadratic equations. A simple equation like, uh, let's say, x squared equals -1, where x would be equal to root of -1. This has no real solution, since the square of any real number is never negative. We must either be content with the statement that this simple equation is not solvable, or follow the familiar path of extending our concept of numbers by introducing numbers that will make the equation solvable. That's what we did through history, right? And so we came up with complex numbers, wherein uh, we introduced a symbol I, and we said that I squared equals -1. Of course, this object I, the imaginary unit, has nothing to do with the concept of numbers uh, as a means of counting. It is purely a symbol subject to the fundamental rule that I squared equals -1. And its value will depend entirely on whether by this introduction a really useful and workable extension of the number system can be effected. Since we wish to add and multiply with symbols or the symbol I, as with an ordinary real number, we should be able to form symbols like 3i, negative I, something like 2 plus 5i. In general, something like uh, a plus ib, where a and b belong to real numbers. Then, for example, if we look at the different laws, such as commutative law, uh, what was the other one? Associative and distributive. If these symbols are to obey these laws of addition, multiplication, division, and subtraction, or the main operators on numbers, then they will form a field. So let's look at two complex numbers. Let's say a plus ib and c plus id, and we are saying that they obey the known laws, that is commutative, associative, and distributive. Now if we put on operations on them, let's say a plus ib plus c plus id, we end up with a plus c. Now you see, we are doing this because they follow these laws. uh, Sorry for that. Yeah. Now if we apply subtraction, since they are distributive, that will be this, right? Okay, now let's do multiplication. That'll be ac plus I. Now we get an I squared terms, that is I squared term, that is negative 1. uh, right. Now let's look at division, right? What we do in terms of division is we need to simplify the uh, denominator. So we rationalize with the denominator so that we can knock out the item from the denominator and get a much more desired answer uh, to the operator. That'll be AC. Okay, it's P plus, right, upon, this is the algebraic formula. A plus b times a minus b is a squared minus b squared, so that become plus, since I squared equals negative 1, right? And this will be bc minus ad. So the thing common in when we apply all these operations on complex numbers, on two complex numbers, we get back complex numbers, right? So complex numbers form what we call as a field. And the field of complex numbers includes the field of real numbers as a subfield. For complex number, let's say a plus I 0, this will just be equal to a, is regarded the same as the real number a. On the other hand, a complex number of the form 0 plus bi is bi, which is purely imaginary, imaginary. And you can see how we came up with something such as the complex numbers. And and to be fair, complex numbers are used in a lot of places like quantum mechanics, electronics, to solve a lot of things. And in general, they can be regarded as real numbers because they have been very helpful. And this was just an overview on how we came up with or why did we come up with complex numbers. In the upcoming videos, we'll be looking at the geometrical interpretation of complex numbers, and one of my favorite theorems, it's called the De Moivre's theorem, which is also pretty interesting and very useful in terms of understanding how to solve various other problems. Until then, thanks for watching, and I'll see you in the next one.